podstate poviem len toľko, že toto je prvý zo seminárov, ktorý tak tradične organizujeme, takže máme tu čest otvoriť tento rok. A myslím, že viac tomu bude vedieť pani Mária vedieť povedať, že o čo vlastne išlo, a potom by som už nechal slovo teda Lubošovi.
No, takže ja budem pokračovať, ale poviem asi tak iba 2 alebo 3 vety, lebo všetko ostatné sa dozviete od Luboša. Proste ide o to, že on spolu so mnou bol na zatiaľ 2 pobytoch v Cukube v rámci secondmentov, ktoré sa týkajú projektu SWORD. O čom je projekt SWORD, o tom som vám hovorila už pred rokom alebo tak nejako. No, jednou súčasťou toho projektu SWORD bola aj naša škola, letná škola NATO, ktorá bola teraz začiatkom júla, nie teraz, ale minulý rok, začiatkom júla v Smoleniciach, a tam bolo niekoľko ľudí, ktorých tu nám teraz vidím, vrátane Pánovica a Jara a ja neviem koho ešte. No a na tej škole bol jeden z profesorov, Jadový. To je profesor z Kalifornie, pôvodom z Číny, a ten navrhol Hirošimu, ktorý bol našim hostiteľom v Cukube, aby sme niekoho vybrali, kto môže prísť akože na invited speaker na Photonic West, ktorý bude teraz, a tam to je už napísané, v San Francisku od 25. januára. No a my sme si povedali, že dáme tú príležitosť Lubošovi, a toto, čo budete teraz počuť, je vlastne výsledok tých jeho, nehovorím, že celý výsledok, ale vybrané výsledky jeho práce za tých 5 mesiacov, čo zatiaľ strávilo v Cukube. Takže buďte nemilosrdní, roztrhajte ho, lebo potrebujeme, aby sa prezentovalo čo najlepšie. Čiže vaše otázky nech sú akékoľvek do toho.
A bude to v angličtine z toho dôvodu, že to bude prezentovať nejaké dokumentárne konferencie, svetovej konferencie. Toto je už
vlastne tá prezentácia, ktorá odznie tam. Čiže bude aj po anglicky, aj všetko, ale prosím vás, diskutujte.
Dear ladies and gentlemen, my name is Luboš Podlucký, and today I would like to present my work called Biocompatible sensor pH sensor based on Chitosan IPNs and Polystyrene Colloidal Photonic crystal films. Very long. Okay, first thing I will talk about the content of my presentation, introduction. I will talk some basics about the 2 parts of the sensor, so the Chitosan and the photonic films. About some theoretical basics, Chitosan, IPN, what is IPN, what is Chitosan IPN, photonic crystals, colloidal photonic crystals, and then I will talk about the fabrication procedures of each part of the sensor and the whole sensor, and then the analysis and the function of the sensor and conclusion. So, introduction. What is the point of this sensor, or how it works? It essentially combines the ability of Chitosan to swell under different pH values in a different way with the color-changing ability of the photonic crystal film, which is deposited on the flexible rubber or silicon sheet. And the potential use that we wanted to, here's why we wanted to make it, is it will be used as wound dressing, because in wounds, as you know, when the wound it's normal, or like the pH of normal skin is around 5.5, and when it gets infected, and start to swell, it starts to create exudate, the pH rises. So the idea was that we would put it on the wound, it would start to swell, and with rising pH, and it would change color. So we would see that, okay, the wound is infected, or no, it's not infected, and it's healing properly. That was the idea. But before I get into it, let's start with some basic introduction about the parts that I said before. So the first thing I'm talking about is chitin. What is chitin? Probably everyone knows. It is the main renewable polysaccharide in marine environment. The second most abundant on Earth, right after cellulose. It is contained within cells, cell walls of fungi, and in exoskeletons of arthropods, like shrimps, lobsters, crabs, etc. Research into chitin started in the early 18th century. Commercially, it is produced from these things, shrimp, lobster, crab, their shells, which are a major byproduct of the seafood industry. So there's lots of it. The structure of the chitin is comparable to cellulose. It is hard, quite solid, hydrophobic, non-toxic, or slow toxicity, is inert to gastrointestinal tract of mammals. The biggest issue, well, it was used a bit in some biomedical applications, but the biggest issue of it is low solubility. And that's where chitosan comes in. Chitosan is essentially produced by the acetylation of chitin using sodium hydroxide. So you take chitin and put it into sodium hydroxide, it starts to acetylate. And once the acetylation reaches over 50%, we get chitosan. Chitosan was first produced in 1859. The started production started in 1971. It has a lot of amazing attributes. That's why it's widely used. So antimicrobial, antifungal activity, beer sensitivity, that is the one we use. And since we want to use it for wound dressings, it is important that it's biocompatible and also non-toxic. So potential applications, many applications, chemistry, biochemistry, biomedicine, wound dressing, drug release, whatever, a lot of it. There are two main attributes of commercially available chitosan. The first is the acetylation degree, which essentially is defined by the percentage of free amino groups. So it's the over 50% up to 100%. And the acetylation degree influences some attributes of the chitosan, such as tensile strength of the films and the ability to chelate metal ions. But we don't really care about that. What we care about more is the molecular weight, which is divided into three different groups: low, medium, high, by kilodaltons, which influences the mechanical properties of the films and hydrogels, membrane pore size, antimicrobial particle size, drug release effectiveness. When you buy chitosan, it usually comes as a white or like yellowish, brownish powder, depending on the molecular weight. If it's higher, then it's a bit more brown or yellow. But you can concentrate in flakes, and then you can produce and fabricate it in different forms, such as films, like we did, or nanoparticles, microparticles, nanofibers, composites. Again, but the issue with pure chitosan is that it dissolves at low pH. Like if you put it in even pH 4, pretty much the film converts back to hydrogen, which isn't really beneficial for us. And it also lacks mechanical strength. That's why we use something called interpenetrating polymer networks. What is IPN? It is a polymer comprising of two or more partially interlinked networks which are not covalently bonded together. They are usually bonded with either hydrogen bonds or van der Waals forces, and they cannot be broken unless the chemical bonds are broken. There are two main ways of fabricating or synthesizing these IPNs. One is sequential, which first you polymerize the first network, create with monomer crosslinker, and then the second one, and create the IPN, or the simultaneous, which is just together, right? This is the one we use pretty much. What about Chitosan IPNs? Chitosan IPNs are, well, Chitosan with some crosslinker. These are some of the crosslinkers used. There are many of them. Which one do you want to use depends on which application. Right? Different applications would require different crosslinkers. Some of them are like TIOS, tetrahedral orthosilicate, polyacrylamide, glutaraldehyde, aftergenidine, citral, and so on. So there are many of them. We used TIOS. Here you can see a schematic representation of such IPN with two of those networks like intertwined together. And we also use glutaraldehyde, which you can see the formation here. The problem with glutaraldehyde is it's very toxic, but we try to use as little as possible, so to keep the toxicity low. And technically, the glutaraldehyde shouldn't come in contact with the skin, with the wound, so it might be fine, might not. We're trying to find a way how to remove the glutaraldehyde, but for now, for this application that we tried, they can still glutaraldehyde. That's why I'm presenting it with it. Then the second part of the sensor was photonic crystal films deposited on rubber sheets. So what is photonic crystal? I found some definition. Nanostructures with periodically changing refractive index that are designed to affect the motion of photons in the same way as the periodic potential semiconductor crystal affects the electron motion by defining the allowed and forbidden band gaps. Essentially, periodic change in refractive index. It can be in three different geometries: one direction, two directions, and three directions. So the 1D, 2D reading. Here you can see the geometric models, and we also have some illustrations of like actual fabricated photonic crystals. Fabrication of 1D is usually done with like film light deposition, where you intertwine, like you fabricate different films with different thicknesses and different refractive index on top of each other. With, for example, PECVD, it's Bragg rating, if you know. 2D is usually done with photolithography or by drilling holes, and 3D is by either stacking the 2Ds on top of each other or by self-assembly of particles. Here you can see good pilot structure, but that's not what we use. We use the self-assembly of particles for colloidal photonic crystals. Colloidal are essentially made from colloidal nanoparticles, which self-assemble together to create a crystal lattice structure. In nature, you can see opal, not opal, and you know that when you like turn the opal, it changes color, right? Because that's how the photonic crystals work. And then on the angle of the light, the color changes. Here on the right is one of the deposited coated opal film in the laboratory of Professor Photonic. And on the right, you can see the self-assembled particles, right? SEM image of the particles. Yeah, so what does determine the color of the film? If you want to deposit a film in a certain color, how do we change the color? Well, the color is governed by the Bragg equation, which is here, where the M is the order of diffraction, which is not important that much. The lambda is pretty much the color that we see, and then what it influences. The first thing, okay, it's the effective refractive index of the particles and the material surrounding the particles. So it could be gas or water or whatever, depending on what we have there. The second thing is the angle that we look at it, right? And the third thing is B, which is the distance between particles, the spacing between the particles, which for the closed spec array that we have is related to the diameter of particles by this simple definition. So the distance is equal to 0.86 times the particle diameter. So the color, very easy. Essentially, how we change it, the color depends which color we want to deposit with what kind of film. We can either change the effective refractive index, but that remains the same because we always use polystyrene particles, and we also always use IPNs for infilling of particles, so that is always the same. So we change it by the distance between particles and by the size of particles. That was the end of the introduction. And now for the fabrication. The first thing we wanted to fabricate were the films. So how do we fabricate? First we create hydrogel. Chitosan hydrogels is made by cation solution, polymerization technique, and acidic solution. What it means is that we put chitosan into acetic environment. This time we use acetic acid. So if you wanted to make only pure chitosan films, we only use the first hydrogel. Then we would drop cast it into Petri dish and dry it in the oven for 40 degrees for 22 hours. But that was the first experiment. We found out that chitosan isn't good enough. So we then combined it with TIOS and then we also combined it with ultraldehyde. These are the materials that we used, all from Sigma Aldrich. So low molecular weight chitosan, tetrahydroxyl ultraldehyde. And for, okay, so that was the chitosan fuel. Now for chitosan TIOS, we used two more solutions. We combined TIOS with, we dissolved TIOS in diluted TIOS in methyl alcohol. We let it stir for 30 minutes. And we also diluted or created this hydrochloric acid solution, also for 40 minutes, stirring for 40 minutes. After 40 minutes, we've combined number 2 and number 3 together to create TIOS solution, which was then stirred for another 24 hours alongside the chitosan solution. Then after 24 hours, we combined both of them together to create the hydrogen solution, which you can see here. And then they were another 48 hours, or maybe even more. And then we cast it and dry it, and we got the film of chitosan TIOS film. And for chitosan TIOS ultraldehyde films, because as I said, IPNs use 2 or more networks, so we used 3 networks in this case, because what we found out is that if you want to make high mechanical strength, logically you would use more crosslinker, right? So if you increase the concentration of TIOS, you would get better films with higher mechanical strength. But if you increase it too much, the film starts to break and starts to create flakes. So instead of creating nice monolithic film, like here, it will start to break and create like flakes, which wasn't really good for us. That's why instead of increasing the TIOS, we just added a little bit of ultraldehyde, really like a tiny amount, because we essentially took 0.5 milliliters of ultraldehyde solution. We added it into 10 milliliters of water. And then from that solution, we also only took 0.2 milliliters and added it into 50 milliliters of chitosan TIOS hydrogel. So the concentrations are really, really low in order, to keep the toxicity as minimum as possible, while still increasing the mechanical strength of the films to make them strong enough for our sensor. The next thing we fabricated were the polystyrene photonic crystal films. They were done by, first we Professor Fudoshi fabricated the monodisperse 210 nanometer particles for this case, because the first experiment we used green films. We'll see it in the next slide. And for green films, we used green to red, red to green, red and green films. And for that, we used 210 nanometer particles, which were synthesized by emulsion polymerization of styrene monomer in presence of SDS, significant non-active. And then we used this solution, this suspension, and deposited it on flexible silicon rubber sheet using this equipment. Essentially, as you can see, you take a substrate, we attach the rubber sheet on top of it, and then you dip it into the suspension. But before you dip it into suspension, we also treat it with plasma to increase the hydrophilic properties, so the suspension with the polystyrene particles sticks better to the substrate. And we also added covering coat on top of it, because when you deposit it this way, the deposition takes a lot of time, about 4 days, because it's very slow, right? If you want to have nice homogeneous film, you need to slowly pull it out or pull down the vertical stage, depending on which where it was used, which equipment, because there are 2 different ones, but they are the same. So in order to prevent evaporation of the suspension, we added the covering coat on top of it, because if the suspension evaporates, it would increase the concentration of the particles in the suspension, which would make the film grow thicker and thicker as you deposit it. So here you would start with some thickness, and at the end the thickness could be like double or triple if you don't nullify the evaporation from the suspension. Here on the left, you can see that we started with the suspension, then we deposited it on the film. But if it's there, just like this, it's very easy to remove it, right? You can like scrape with your finger and you remove it. So you need to fix it, and for fixing it on top of the flexible substrate, we use the polydimethyl siloxane elastomer, PDMS. First, so you infill it, and then you let it dry in the oven at 60 degrees overnight. Remove the PDMS from the top, the additional, because you need to cover the hole as much as possible. And then you infill it again. And then again and again, and every time you infill it, the distance between the particles increases. And why do we need to increase the distance? Because if you stretch it, then the particles will go back, right? So they are like this, with some distance between them, which has some color. In this case, it would be red. And if you stretch it, they go closer together, which will turn back to green. Here you can see. So this is just the color change based on the angle of observation. Again, I added the equation. So when you change the theta, which is the color of the angle of observation, you can see that the color changes. That's fine. As I said, we start with green film, and every time we infill it with the PDMS, slowly starts to turn the color to orange or red, and it becomes this orange in color. And then when you stretch it, it goes back to green. So that's why we need to infill it as much as possible to allow high color change, right? Because the more you infill it, the farther the particles are, and then when you stretch it, they go back, which means that the more you infill it, the bigger the color change, maximum color change possible for this film can be. Okay, next thing is the overall design. So here you can see the model of the design. Here is the top photo of the sensor. On the bottom was plastic mesh, which allows the pH solution that we use to analyze the swelling properties to go in. We also added dialysis membrane to make sure that the chitosan doesn't leak out from the bottom. And the next step was the chitosan films stacked on top of each other. First we started only with one, then we found out that the one doesn't work, so we added more. I will show it later. And we added the plastic frame around to minimize the swelling in unwanted direction, so it only swells up as much as possible. We added also black cloth to make the color change more visible, and on top of it there is the photonic crystal sheet covered with metal frame like this, so you only have this hole, and underneath is the chitosan, so when it swells, it pushes and changes the color. The first analysis was swelling to find out how much the chitosan film swell. For that we used percentage based on the weight percentage. So original mass before swelling and then mass after swelling calculated through this equation. After swelling and drying, we cut the samples to 1 times 1 centimeter. Here you can see the picture, right? Added the pH solution, let it absorb as much as possible for some time. How much time? Well, first we wanted to find out how long does it take to fully swell. For the films to fully swell and to stabilize. So we did this experiment with 4 different pH values, 2.5, 4, 7, 9. In one film, it was the dissolvation of this, the chitosan glutaraldehyde film. You can see that the lower the pH, the higher the swelling, and overall the swelling stabilized for most cases around 7, 8, 9 minutes, right? Like here, around here, and except pH 4, which stabilized around 12 minutes. And then we also did the second experiment where we compared the swelling of chitosan glutaraldehyde film and chitosan film. We can see that the chitosan film has much higher swelling, percentage of swelling in every single case, especially at 2.5. But it wasn't that good because the swelling was just too much to get to the point where when I tried to pick it up out of the petri dish, it would just like the tweezers would go through the film, like it was almost a hydrogel, even in this case. So the next step there was the analysis of swelling to see how it swells and if it changes with pH, which we found out that it did. Next we wanted to analyze was the color change based on pressure, right? If pushing it really changes the pressure, changes the color. So we did this small experiment with pressure chamber, a tiny pressure chamber. Here we have a pressure meter and a syringe. That when we pushed, here was the sample. As we pushed and increased the pressure inside, it started to swell from the bottom, and the color started around 620 for 3 different hole sizes. That's not that important, but we can see that with increasing pressure, the color started to change. And just a quick little experiment to see if it works. And then we combine them together. So this is the actual sensor. First, we wanted to find out, as I said, if we started with one film. We found out that when you use the first film, then you start to put it into different pH values, different times. It changes the color, but not that much. So we started around 628, and the minimum value for the one film was around 605, which wasn't enough, of course. So then we tried with 5, it was better, and then we tried 10. Films stacked on each other, each film was around 120 micrometers in thickness. We can see that the 10 films was much better, like the color change got better and better with decreasing pH and increasing time. So it was dry sample, and then 1 hour in, one film, 1 pH, 3 hours, and so on. It decreases. Here we can see the peak shift, how it changed between the original value at dry and the final value of the pH at some time, certain time. So you can see that the maximum shift was around 55 nanometers for the 10 films, and for the one film it was only like 22. For the 5 films it was like 32, so it wasn't that good. That value is like from 10. And we also compared the 2 different films with Chitosan TIOS and Chitosan TIOS ultralight. And if you remember, the Chitosan TIOS had much higher swelling percentage. But when we did the experiment with the actual device, where we added the 10 films of one and the other into the device and tried to the sensor, tried to measure the wavelength at different pH values, we found out that the TIOS ultralight has actually higher peak shift. And I think the reason is that the swelling was so high and the mechanical strength of the Chitosan TIOS was a bit low that some parts of the film actually somehow, I don't know why, how, but they leaked into the pH solution, because when I was measuring it, I could see that the solution got like murky. So you could see some like particles in it. So I think the Chitosan TIOS in terms of mechanical strength and the swelling was too strong, too weak in terms of mechanical strength and too strong in terms of swelling. That's why we needed a higher mechanical strength, and that's why the ultralight are right now better. Yeah. Now we can finally see some pictures of the color change. This was the Chitosan TIOS film. I only have 2 pictures. So this was the dry device, and this was after 3 hours in pH 7. You can see that it's slow, and it went from orange to like a bit like orange green. So this wasn't as good, and then this one was better. Here we went from, but yeah, this is orange, then became a slightly more green, and then the pH 4 and pH 2.5 became fully green. But the color change between 4 and 2.5 was almost invisible. Like when you look at the peak shift here, between 4 and 2.5, the peak shift was only about 5 nanometers. So, and even when you look at it, the change was almost invisible. That's why I only included 1 picture. It was pretty much the same. So there wasn't much color change between 4 and 2.5. But between these, you can kind of see that there is some change. It's not much. It doesn't work as well as we hoped. We hoped for more visible color change, especially in this region between like 5 and 7 or 8 for the home dressing application. But yeah, the biggest change is obviously from dry to something. Always, so we could always see the change, right, between dry and anything. Because always went to started to go to be green. And these were the experiments for the red to green. We also tried different experiment where we went, okay, so what if we start with invisible, quote unquote, meaning infrared films, and then we turn it into red film. So this time we used 240 nanometer polystyrene particles. The PDS and Master was the same, swelling and filming. As you can see, we started with red, and as you swell and infill and swell with the PDMS more and more, it turns from red to infrared, so invisible to the naked eye. Here you can see how the peak shifted from the original all the way here to the third filming, here as well. And then it looked like this. With only one experiment, you can see the change in peak position, and you can see here the pictures. So this was dry, which was more or less black. You can see a bit red because the film isn't like 100% homogeneous, so you don't get the color everywhere exactly the same as when it's like slightly red still. Then it turned more red, and then also at the 2.5 it was like fully red. So this one looked pretty good as well. And we also did the same at the other side of the spectrum. So for UV films, this time we tried to go from blue to violet. So when we fabricated, we used 150 nanometer particles, started at ultraviolet, that's why it's black or looks like black. Then when you start fixing it, swelling, it turns blue or violet. Here are the spectra of these two. And here you can see the measurements. The UV film wasn't that good. I only have two measurements for dry and then for 2.5 pH because that was the highest change, and even during the highest change, the higher difference, with swelling, the color change is very negligible. Like here is a bit. Here you can see it's blue and it turns slightly more like dark black. But this is the maximum, and you can see even the peak like barely changed. The UV films are that good. I think the best ones were most like for our application is either infrared to red or the red to green. Those are much better than the UV films. And yeah, that's it. That's the conclusion. So we tried to fabricate a pH sensing device with two different films. We tried them out. We found out that the TIOS, the Chitosan TIOS glutaldehyde was better than the pure Chitosan TIOS for our application. The peak shift, however, the biggest problem is that the peak shift between different pH values was kind of low. So it wasn't really working as well as we wanted to. But the maximum peak shift was obviously between the dry and any wet. So if you have dry film and then you would put it in any kind of solution, that was the biggest change always. Here, right? You can see the first peak was always the biggest, right? So from dry to any other color, it was always the biggest. So it would, instead of working as a pH sensor, it would probably work better as like a wetness or humidity sensor or something like that, and dryness. And here I added a picture of the different films, different colors that we used. That's it. Yeah, thank you for your attention.
38 minút.
Áno, musím to skrátiť o 10 minút.
A budú otázky v slovenčine či angličtine teraz? To je také neformálne.
Toto je neformálne.
Toto už nenakrúcané.
Áno. Ja tu mám rád veci, ktoré tam treba trochu pomeniť. Na to si musíme sadnúť vy dvaja.
Otázky? Otázky do tej.
Áno.
Tak môžem aj začať teda. Z formálneho hľadiska myslím si, že je to pekné, aj to dúfam, budem mať úspech na konferencii, len treba si dať pozor trošku zrozumiteľnejšie, lebo tu je zlá akustika v tejto miestnosti. Hlavne pre mužských hlasov, už sme tu mali exportáž, to zmeral, čiže to sa dá ospravedlniť, ale aj tak bude veľká sála, veľa ľudí. Môže sa stať, že hlavne pri chemických názvoch, že a teraz, no, tí ľudia tam budú asi chemici a oni na to môžu byť citliví, alebo to je jedna vec. Druhá vec, tak možno taká rada, že by vás zvykol počíslovať slajdy, lebo sa oni budú pýtať, hej, a teraz ako sa vrátite k tomu. Čiže to je taká drobnosť, to by tam mohlo byť.
No ešte počet,
možno
celkový počet.
Možno trošku hlasnejšie, hej. No a teraz k tej akože vedeckej časti. Tak tam som sa chcel viacej veci spýtať. Jednak to, čo ste tam ukazovali, také 4 časti, to je kaučuk, alebo čo to bolo? Tam bolo tak, nevedel som to prečítať, tak ako keby, no tie 4 hore, dole, doľava, doprava. Ešte predtým to. Na každom jednom obrázku. Proste tie upevnenia toho senzora. To je len upevnenie. Čiže to nemá nič so senzorom.
To som mohol, hej, to som spomenul.
Dobre.
Na tom jednom obrázku to máš tam popísané. To, čo bolo predtým, tam boli...
Nejaké kaučky tam bolo napísané.
To na skúšku.
Neviem, čo to je. Dobre. Potom ono teda dobre tomu rozumiem, že tieto teda chitosanové zložky toho semena sú v podstate citlivé na akúkoľvek vlhkosť. Čiže v podstate po nejakom čase, keby to bolo aplikované na ránu, to meria aj vlhkosť, bez ohľadu na to, či je infekčné alebo nie. Čiže to nejakú zmenu hotľaka ukáže a môžu byť falošné, ako keby poplatí. To je jedna vec. A druhá vec, na tých experimentoch bolo ukázané, že ono po 4 hodinách to zmenilo pravdu. Ale v realite asi treba tú citlivosť zlepšiť, že 4 hodiny byť už v infekčnom prostredí už pre obväz asi je veľa. Alebo nie?
Naopak. Treba dlhší čas, lebo...
Dlhší čas, aby... Aha, čiže práve naopak, že treba sa urobiť tak, aby čo najdlhšie vydržalo. No kvôli vlhkosti, hej, ale kvôli tej pH.
Aj kvôli tomu pH, lebo keď to máte akože na tej ráne, tak tomu pacientovi nebudete kontrolovať.
Áno, takto to je. Čiže čo najviac, aby to vydržalo.
Čiže raz za deň hodiny, by som povedala, 12 hodín a tak.
Dobre. No ešte som mal zo pár otázok, ale som zabudol, tak ja si spomeniem potom.
Ako tú náču sa mi veľmi nepáči, že vy tam síce hovoríte, že meš, ale keď sa na to takto pozerám, ja viem, ako to vyzerá v skutočnosti, samozrejme, ale keď sa na to pozerám takto, tak to vyzerá ako súvislá vrstva.
Áno.
Čiže bolo by asi dobré nejako nadzorovať.
Ale akože takto, keď sa na to pozriete, tak by to bola súvislá vrstva, ono je to než z tejto strany, čiže...
Áno, to je
hej, že áno. Ale hej, viem, čo ste, aby som to tu naznačil, že je to akože, vieš,
Trošku dýchajte potom pri tom rozprávaní.
áno, len som, hej, mám toho veľa a aj tak som to nestihol, takže...
By som bol nedal ti moc priestor na odpoveď, kolegovia, ale jednu takú otázku, že farba nie je vlastnosť povrchu toho telesa. Je to beriem z fyzikálneho pohľadu. Ale nebolo tam nič povedané o tom svetle, pri ktorom vlastne kontrolujeme to znamená tie podmienky, za ktorých vlastne verifikujeme, čo sa tam stane. Ja som to spomínal.
Viacej zdôrazniť, že to tam súvisí s tými fotonickými štruktúrami. Tam je to svetlo podľa tej častice, veľkosti častice, tie farby. To tam treba oprať, lebo to tam bolo, ale nevýrazné.
Áno, ale akým svetlom sa na to vlastne pozerá?
Bolo to pod viditeľným svetlom fotené a merané to bolo spektrometrom na normálnou sondou.
Luboš, ja som pozerala na tie senzory, ktoré sú, a oni sú dané, že suché 3 hodiny, tak 3 hodiny. Takže reálne, keď mám ten senzor na nejakej rane, kde sa to pH s časom môže meniť. Bude sa mi meniť potom aj tá farba toho, alebo už to bude nejakým spôsobom nasýtené pri tom pH 9 a keď sa mi zmení na kyslejšie prostredie, či mi to odrazí potom tú farebnú zemi, lebo tie fotonické štruktúry, oni sú rozmerovo veľmi malé a keďže je tam vlhké prostredie, ono sa mi to môže nejakým spôsobom aj deaktivovať, alebo potupiť.
To je dobrá otázka. Ja som... Keď som to meral, že som to išiel, že späť a tak mi to vychádzalo, ale nevyšlo, neznižilo sa to späť na tú úroveň, ako to bola predtým.
Čiže keď idem z kyslého do zásaditého, nebudem vidieť tú farebnú zmenu.
Vieš vždycky vidieť, ale keď si ušli, že som napríklad kyslého zásaditého a späť do kyslého, tak už späť, keď to ide, tak už to nepríde na tú istú hodnotu, ako to bolo na začiatku.
Nie je reverzibilné.
Nie je to 100% reverzibilné, že by to vyšlo trošku vyššia hodnota.
Ale predpokladá sa, že ak sa niekedy takéto senzory uvedú pod taxe, no tak to budú jednorazové materiály.
Áno, malo by to byť skôr také, že vidíme, že sa to pokazilo, tak ideme do si.
Jasné, a už to bude kontaminované, tak nemyslel. A výrobná cena sa dá predpokladať, že to bude nejaký opakovaný proces, ktorý sa bude dať lacno predať, lebo to je výsledok toho, že áno, dlhé hodiny experimentu, ale keď už to funguje, to know-how, možno keď to je patentované, že potom vlastne dá sa to asi vyrábať.
No, akože cenovo to vyzerá, že by to bolo lacné zatiaľ. Snažili sme sa použiť také, hej, akože ten Chitosan je relatívne lacný, fonské kryštály tiež, keď to vyrába Hiroshi, tak je to lacné, hej, ako kebyže to kupujete niekde, tak je to dosť drahšie, ako si sami vyrobiť.
Kebyže to mám už rôzne kontaminované, mám to na rane, čiže tam môže byť krv, iné telesné tekutiny.
Ono to nám na kyslo zreaguje a na vlhkosť.
No dobré, ak mám oxín, nejaké prostredie, krvavé,
krv je tiež...
Nereaguje na krv ako tak, ale na vlhkosť.
No, hej,
vlhkosť na zmenu pH.
Ale myslím, že optické vlastnosti, je to tenká vrstva. Je to tenká vrstva, ktorá môže sa mi javiť ako príjemná. A mám pod tým, dajme tomu, hlieny, krv.
To nevadí,
tak preto sa je vám putovať.
My sme to... Preto ja som tam dal tú čiernu látku, aby bolo oddelené, lebo keď tam je čierna látka, tak potom vidíš vlastne aj tie vrstvy pod tým.
Jasné, OK.
Čiže aby to lepšie bolo vidieť tú zmenu farby. Keď tam nebola, tak to nebolo až tak pekne vidieť.
Ako veľký je ten senzor?
1x1 cm.
Nie, 1x1 je tu na vnútri.
No tak no toľko, 1.
To je ťažké, lebo...
Ja sa pýtam veľkosť, nie?
Veľkosť,
To som videla.
3-4 centy?
No
zatiaľ toto je veľké, ale tak máme aj menšie tie. Lebo my sme to len čo robili na tieto kovové, čo sme mali z tieto frémy.
A v rámci celej tej plochy je tá fotonická štruktúra daná.